you will tell me if is everything okay with you, and then you will do whatever you want. You can talk 10 minutes, half an hour, or what else. I will try to fix if there is any kind of trouble. Usually there is, by checking from time to time my email, but it seems the situation is okay.
It's good. Yeah.
And who wants to start? May I do it for a while? So since long I have some interest, but I have never practically worked on iron, aluminum, and manganese steels, but I have a lot of curiosity. So I've been partly involving in my interest other guys. For instance, Cristophe, she's working for the industrial R&D of ABS-HI. ABS-HI is in Italy, but is leading the R&D center in Metz in France. So myself, I am just a university professor, but in remote times, I usually say in the previous century, I was also the metallurgist of a special steel plant, precisely that one, ABS-HI. And I'm absolutely interested in how to go on with the so-called lightweight steels, and generally speaking. So I'm very pleased to have you from remote, and this opportunity to manage contacts by abroad. This is the one of the few nice things that this terrible pandemic has brought to us. But this is very good. So after saying hello, all the best to all of you, and thank you for being here. We will start. Okay.
Okay, first of all, I would like to really thank you for this invitation, and we are really pleased to be here. And it's a pleasure to meet you all guys through this MS Team meeting. Mm-hmm. So let me say something. Just 1 second, please.
Yeah. I will ask you, can we be informal in our talk? Yes, because we are, if you prefer to do very formal things, it's okay. But I need a time. Maybe I should dress up.
No, I think it's informal.
If we can do something informal, it's better, because then it's a sort of meeting, and so not only presentations. If you have presentation, if you don't have presentation, is okay. And anything is okay. Anything would work.
Okay. We already decide to do this presentation by divide it into parts. The first part, I will give you a really quick introduction about permanent alloys, and then my colleagues, John, Sebastian, Professor Germán, are going to talk about their research. So I will share first my presentation, and then we can move on with the other one. It's really a really brief presentation. I cannot see my PowerPoint.
This is normal. Yes. Okay. There is always something difficult, but nearly always it's always possible to solve. Please.
Okay. Can you see my screen?
Yes, for sure.
Okay, yes. Perfect. Well, first of all, my name is Oscar Zambrano. I will provide a really quick background of myself. I did my bachelor in materials engineering, my master in mechanical engineering, and my PhD in materials engineering at the Universidad del Valle in Colombia. Then I did postdoctoral in Brazil, a couple of internships in Switzerland at the École Polytechnique Fédérale de Lausanne. And recently, well, not recently, 2 years ago, I joined the National Research Council Canada. And I'm here to provide this quick overview about the lightweight steel. So I put the title, Ultra High Strength and Ductility FeMnAlC Steels as Potential Replacement for Conventional Steels. So conventional steel, there are many, but I decided to put here the stainless steels. And we already know that the chromium forms a stable passive layer, and the nickel is a gamma stabilizer. Both of them are expensive elements. So what are the iron, manganese, aluminum, carbon steels? Basically, it's a kind of new alloy which consists in manganese, aluminum, and carbon. And the manganese has the same effect as nickel, because manganese is a gamma stabilizer, is a solid solution strengthening in the substitutional way. The aluminum in this case produce a stable passive layer similar as chromium. The aluminum also is a ferrite stabilizer, favor the K-carbide precipitation, and due to the very low density, of course, it will decrease the steel density in a remarkable way. And the carbon is a gamma stabilizer and solid solution strengthening in the interstitial way. But the main difference with conventional alloys is that manganese and aluminum are cheaper alloy elements, and that is really important in the market. Here is a brief figure or picture about how the interest in these alloys has become important in the last 15 years. Let me close here. So this is a chronological result in Scopus using two different words, iron, manganese, aluminum, carbon, and the lightweight steels. So we can see from the last 15 years, the interest is going up drastically. Some mechanical properties of these manganese alloys that will allow us to put us in a context, in a better context. So here in the y-axis, we have the elongation, and the x-axis, we have tensile strength. So we have different families. Let me use a pointer. We have the aluminum, magnesium, titanium, and the whole range of carbon steels, including different heat treatments. So what makes special these materials are the good combination between elongation and tensile strength. So we have a family of these alloys with different manganese contents, different aluminum contents, and that makes really interesting different applications. Here is a graph of the mass density versus aluminum content. And of course, as we increase the aluminum content, we will have a drastic decrease in the aluminum, in the density, the density reduction. So we can achieve density reductions about 18%. That's mean close to 6.5 grams per centimeter square. When compared with the conventional steels is 7.8. So we have a really interesting effect about the aluminum in these alloys. And that's the main reason that these alloys are called lightweight steels. This image was took from this research. Well, basically, they developed a new manganese aluminum alloy. And we can see here how the properties as a function of factor toughness of gel strengths are when compared to other families. So, for instance, let's say austenitic stainless steel is this round circle here, pink circle, sorry. And so the austenitic steels have a really good factor toughness, but the gel strength is below 1 gigapascal, but it's pretty good anyway. When we compare with high entropy alloys, we can see that this is the new trend in the physical metallurgy, the high entropy alloys. So we can see here that the fracture toughness are really high, but the gel strength is still too low. So if we make the same analysis to other materials, we can see how the manganese steel stand when compared with them. So with this material, it's possible to get a really high fracture toughness while keeping the gel strength. And what is the main reason of these astonishing mechanical properties? Basically, when we see the true versus strain curve, for different manganese aluminum alloys, we can see that up to the gel strength, they behave similar. But after, when the plastic deformation starts, there are different mechanisms that allows these materials to gain a strain and gain stress. So this is a strain hardening behavior, really quite interesting. So let me, and the reason behind that is with this alloy, we can control the chemical composition and the stability of the austenite. So basically what I mean through austenite stabilization is we can control the chemical composition to make the austenite less stable or more stable. And that is reflected in different deformation mechanisms. So if we make the austenite really unstable, we can prone the transformation from austenite to martensite. If we make it more stable, but not too much, we can favor the formation of twins, mechanical twins. And if we make it too much stable, we will have the formation of microbands made of dislocation arrays. So these deformation mechanisms, those are special deformation mechanisms that we can control by the chemical position, temperature, and this will determine how the mechanical properties are for this material. So recently, I just want to give you a really general overview about the current state of FeMnAlC alloys in different industry. So in the energy and transportation industry, the world fourth largest steel making company it's been doing some research in these materials. So they patented in 2013 a patent about these materials. And currently, if you can check the website, for instance, they are producing these liquefied natural gas vessels. So currently, they are producing these vessels using this kind of alloys. For instance, in the automotive industry, Volkswagen did obtain a patent in 2010 about replacement of conventional alloys to the seat frame. So they are using this kind of material for the seat frame. Similarly, ArcelorMittal patent in 2020 a method of production of these alloys for the body car frames. And the reason of that is because when there is a car accident or a crash, the high energy during that process can be absorbed by this material. Let me go back here. Can absorb this by this material by strain hardening. So it becomes harder, while also provides some deformation. So that's the main reason of this choice for producing this material. Also, Tata Steel patent in 2021 different methods for producing this kind of alloys. In 2019, was patent in the Army industry contest this patent about the high aluminum manganese steels. So currently, they are studying, they are exploring this material for ballistic applications. For instance, for tanks, armor. In the mining industry, for instance, CAT patent in 2019 different alloys based on iron, manganese, aluminum, and carbon to replace shovel tooth or shovel teeth if we are talking plural. So basically, they are exploring different new materials that can withstand longer times than conventional alloys. So in my perspective, the future direction and current challenges are the production of this alloy. Still, there are many challenges there. The processing itself and the applications. So there are too much to explore about this material. Basically, now they are being used for body car frames, but there are many applications that these materials can be applied. So that's what I wanted to say, and I will let the floor for my colleagues, Sebastian, John, and Professor Germán.
Okay, thank you so much. It's a very nice, quick presentation that takes a very interesting perspective. Okay.
Okay, thanks.
Hello, everyone. Continuing to Oscar presentation, the Professor Germán, John Duran Perdomo, and me, I talking about a presentation of FeMnAlC Steel. Professor Germán.
Dime, Sebastián.
Tienes la palabra, profe.
Okay, thank you. Well, this is a work that we are performing now. It's a project that we presented to our science minister and was approved, joined with a local industry, called Organización Hércules. They are producing sugarcane goods, and the project has the objective to produce iron, manganese, aluminum, carbon steel in order to obtain the best properties to produce sugarcane goods. Is the project in which we are working now, okay? And John, Fernando, and Sebastian are the students, the doctoral students that are working in this project, okay? Recently, they were in Mexico, in Morelia, in the Michoacán University, producing 4 alloys, those that we found with the best properties, in order to make a semi-industrial production and to melt them in induction furnace and then rolling in place in order to, from this place, produce the sugarcane goods. Okay, this is a small presentation. That's the work that is going to be presented by Sebastian and John to illustrate you our current work. Thank you.
Thank you, Professor.
Okay.
Okay. Very well. About us, Cali is the third largest city in Colombia, behind Bogota and Medellin. It has an approximate population of 2.2 million people. It is relatively big. The city has 2 very characteristic monuments. One is Cristo Rey. Give me a second, please. This is Cristo Rey, a monument similar to Cristo Redentor that is in Rio de Janeiro, and the Hill of the Tres Cruces. According to the history, we made to scare away a demon that in ancient times he was in a tomb. We also have a very interesting church. It is called the Ermita, and some pretty beautiful views, as can be seen in this image. This corresponds to the central area of the city. On the other hand, something very interesting about the city is the weather. Cali is located in the tropical zone near to the equator. Therefore, we do not have season. Along the years, the temperature is within the range observed in this figure. And also, the time that the day and night last are the same throughout the year. As for use, we are researchers who belong to the Universidad del Valle. This university is one of the most important in the country, in Colombia. It is a public university and was founded 76 years ago. The university is divided into 7 faculties. Professor Germán and John belong to the Faculty of Exact Science. They are physicists, and I to the Faculty of Engineering. I am material engineer. Currently, the group that developed this research work are the physical metallurgy and phase transition theory group from the Department of Physics and research group of tribology, polymers, powder metallurgy, and processing of solid waste from the Materials Engineering School. This is a research project developed by physicists and engineers. The content of the presentation is presented below. In this, talking about processing of FeMnAlC Steel, foundry of steel steels, thermomechanical treatment, hot forging, hot roller, characterization, EBSD results, some properties, wear resistance and micro hardness, impact toughness, corrosion resistant, and current investigation and future investigation. Here we will mention some of the most important results of our research, and at the end, we will be willing to answer some of your questions and middle college from the Universidad of Udine. Let's me, please, John Fernando Duran continues.
Good afternoon, everyone. My name is John Fernando Duran Perdomo. I am physicist and PhD student in physical science at the University of Valle in Colombia. I work in physical metallurgy with the Dr. Germán Antonio Perez. In the case of thermal alloys, it's necessary to perform thermomechanical treatment to eliminate the Alcazar state. How you can read in our paper, a long time solubilization treatment of our case eliminate the Alcazar state, but with an increase in the grain size, involuntary evaporation of some elements, as well as interaction of the elements of the alloy with oxygen. Thus, they are exploring two thermomechanical processes for these alloys, hot compression and hot rolling. To cast these alloys, we start with AC 1020 and 1045 steel, ferrosilicon, high and low carbon ferromanganese, aluminum, and copper. All these elements are placed in the induction furnace containing alloy plates like you can see in the figure. Next. There are two thermomechanical treatments that we are carrying out with the alloy study so far. The first is a hot compression deformation while maintaining the furnace temperature between deformation steps, and the second is hot rolling. You can see in the video the hot compression deformation at Hercules organization in Cali, Colombia. Next. In this video, you can see one of the alloy that was deformed under laboratory condition and the École Polytechnique Fédérale de Lausanne. No.
I think you didn't click, Sebastian. Okay, it's taking. Maybe you can repeat.
Next, Sebastian. Like I said, these alloys have been hot rolled. This sample were produced at the Michoacán University in Mexico. Place. you can see different lamination steps are performed. To characterize these alloys, we have used different techniques, including Moldbauer spectroscopy, S-ray diffraction, and backscatter electron diffraction. In the case of Moldbauer spectroscopy, there are three types of hyperfine interactions. The first is isomer shift. You can see a singlet, in this case, one peak in the spectra. The second, the quadrupole splitting, you can see a doublet, in this case, two peaks in the spectra. And finally, hyperfine field with 6 peaks in the spectrum. In this case, one sextet. These three interactions characterize the chemical environment of iron atoms. Next, please. Different phases have been reported in FeMnAlC alloys, including austenite, ferrite, martensite, kappa carbide, beta manganese, and the following carbides. The figure in the left shows an austenite structure of the steel without any alloy elements. When elements such as manganese, aluminum, molybdenum, and silicon are added, it could replace iron atoms, like shown in the figure, where the X represent the different solute atoms. Next, please. The first equation represents the complete spinal decomposition of austenite proposed by Chen. In this, in the second equation, you can see the partially spinal decomposition of austenite that we propose in our paper. Thus, there are 3 austenite, 1 normal or initial, 1 rich, and finally 1 poor in solute atoms. As you see in the figure. Next, please. In this figure, you can see the Moldbauer spectra adjustment with the 3 types of the austenite. In this case, we only have singlets related to the paramagnetic behavior of the austenite. And next, please. In this figure, you can see the value of isomer shift remains with the error bars without considering the treatment performed on the alloy. Next, please. All Moldbauer spectroscopy results were validated by S-ray diffraction. In this case, the Rydberg refinements were carried out using 3 austenite phases with small variations of the lattice parameters. Next, please. In Zambrano's research, Moldbauer spectroscopy has been used to characterize kappa carbides in FeMnAlC alloys. The kappa carbides have a magnetic behavior, sextet or field distribution are observed, while austenite has a paramagnetic behavior, singlet or doublet or observed. Thank you, sorry. Thank you so much. Sebastian?
Okay, continuing about EBSD results. By this technique, the result obtained in the processing by hot forging were characterized, which was approximately 950 degrees Celsius. Here are the one-step deformation results. According to the graph, for both composition, the recrystallization phenomenon is the same. It is this continuous dynamic recrystallization in a color structure. Due to the one-step deformation condition, it can be seen that the sample is textured. According to the figure corresponding to grain orientation spread, B and C, there are low degrees of misorientation, which indirectly indicates that they are grains with a low level of dislocation. That is, according to the processing, they are a uniform grain. Finally, a phase map is presented, in which a small ferrite formation is evident, but according to Mossbauer and its right diffraction, this condition do not have ferrite. It is assumed to be a result of improper data indexing. In order to quantify the effect of dynamic recrystallization, this grand size distribution was performed, in which the distribution clearly indicates that at one deformation step in both alloys, there is a process of formation of new extremely fine grain. When looking at the result of the industrial deformation process, large differences are observed. It is important to mention that the industrial deformation process consisted of heating, deforming. This was repeated 3 times, and finally quenching. In the graph, we first observe that the sample after the deformation and heating cycles does not present texture. The dynamic recrystallization process produces grain with random orientation. On the other hand, it is observed that the degree of misorientation of these samples is very low, which corroborates that the condition of this microstructure is that of newly formed grains as a result of the recrystallization process. And finally, this process does not generate phase transformation at the working temperature. As the aforementioned is presented in this bar graph, it is observed that there is a process of formation and growth of grain during the 3-step processing, in which a structure of HZ small and randomly orientation grain is obtained. In summary, at this point, we have studied the dynamic recrystallization behavior of two compositions of FeMnAlC steel with 2 different processing conditions, in which the one consisting of 3 deformation heating steps obtain an optimal structure in terms of engineering application. At this point, the question arises: how is the dynamic recrystallization process when the aluminum content is varied with a fixed manganese composition? Okay, the answer to this question is covered by a research work that is currently submitted in the journal Material Characterization. Its title is "Effect of aluminum content on the dynamic recrystallization of this alloy, this composition, steel during thermomechanical hot forging treatment under review." This was submitted in Material Characterization. What was done in this work was to vary the aluminum content in 0, 3, 6, and 9%. By the way, the processing is by hot forging through 3 deformation heating steps. In this figure, crystallographic orientation maps of the thermomechanical traded FeMnAlC sample are represented. The microstructure of the material does not result in preferential orientation. In contrast, the growth of the arrangement of the grain in front of the crystallographic direction was completely random. On the other hand, the figure corresponding to the grain orientation spread of these alloys is presented. It is interesting to observe that the degree of misorientation of these are low, which coincides with the previous work and indicates that the grain are newly formed by the hot forging process. In addition, the formation of the collar structure is also appreciated, which is a clear indication that this process occurred throughout this continued dynamic recrystallization. Something quite interesting to appreciate is that the increasing of the aluminum content of these alloys generates a grain refinement, We will delve into this later. According to the characterization of this sample via X-ray diffraction and multi-power spectroscopy, only the sample 20 manganese, 9 aluminum is duplex steel, that is austenite plus ferrite. The other are austenite. The small areas that appear in the sample, 20 manganese, 3 aluminum, 20 manganese, 6 aluminum, are due to poor indexing of the date. Finally, the micrograph are shared with annealing twins. In this case, it is observed that the variation in aluminum increases the area fraction of the twins, which is directly related to the increase in dynamic recrystallization. The explanation for the refinement of the microstructure through thermomechanical treatment is based on the following hypothesis. It is very likely that the lower aluminum content favors the rapid generation of difference in dislocation densities between different regions, which generates many sites of recrystallization of the grains. And by continuing the thermomechanical process, the previously formed grains grow at the expense of other and of consuming the density of remaining dislocation, leading to a growth of grain size. On the other hand, in the samples with higher aluminum content, the samples have difficulty generating sufficient dislocation density difference between regions in a short time. Therefore, the creation of numerous nucleation sites for new grains will be facilitated. For this reason, discontinuous dynamic recrystallization can be observed more easily in samples with higher aluminum content. In the case of high aluminum content, the increase in the content of this element for the composition of iron 20 manganese, H aluminum 0.8 carbon steel will favor the formation of second phase. In this case, is ferrite. Therefore, the grain refinement for high aluminum composition ends up being the joint actions generated by the difference in dislocation densities, the nucleation dynamics of a second phase, that is, of the ferrite, and chemical segregation generated by spinodal decomposition. Once we have this work published, it will be a pleasure to share it with you. Okay, up at this point, we have presented the results using hot forging, but it is well known that the mass production of steel consists of rolling processes, either hot or cold. Well, we all have information about hot rolling of these steels. This was the result of an international internship at the San Nicolás de Hidalgo, Michoacán University in Mexico. We studied the processing of this steel by hot rolling, and the results are very promising. The dynamic recrystallization process is very interesting. In this study, the formation steps and temperature were varied. Dislocation plays a very important role in the processing of this steel. The article of this internship is in process. We are characterizing all the results by X-ray diffraction, multi-power spectroscopy, and metallography. The VSD is also scheduled to be performed on this sample. Okay, after talking about processing, we will talk about some properties that we have studied on FeMnAlC Steel. It is important to mention that the microstructural condition of this steel is that obtained from the thermomechanical hot forging treatment in sheet steel. The figure present shows the result of abrasive rubber wheel wear. In this, a relationship is made between the loss of volume and the hardness of the material after the thermomechanical treatment. The results are quite interesting. It is important to appreciate that the hardness of this steel does not depend on the loss of volume. I can be seen that FeMnAlC Steel of high hardness have the highest volume loss. It is also important to see that this is due to the increase in aluminum content. One of the explanations that we have to this behavior is based on the staking for energy. Increasing the aluminum content increases this energy. Therefore, this increase generates a transition from hardening mechanisms such as strip, you can see, tweed, MB, toward other with higher stacking for energy, such as dislocation glide. According to the calculation of the stacking failure energy using a thermodynamic model with the chemical composition, the mechanisms that possibly predominate the dislocation movement in steel with an aluminum is the trip. The increase in aluminum from 3 to 6 indicate that the mechanisms that are possible presented tweed and MB hydrantus with a high aluminum content, which possible the governing mechanism is dislocation glide. It is also interesting to appreciate that the increase in the aluminum content generates hardening of the steel. See the hardness of the materials. It has the role of increasing the strength of the material by solid solution. In the analysis corresponding to the wear surface, we find something quite interesting, and that is low hardness steel, zero aluminum, such as high hardness steel, 9 aluminum. Low aluminum and high aluminum, in general terms, they present microcuding, while the half aluminum, one high microplugging. This serves as evidence to continue with the hypothesis that plasticity hardening mechanisms improve wear resistance and the surface level. On the other hand, we present the effect of aluminum content on impact toughness. It is important to note that the increase in solid solution hardness in FeMnAlC steel affect their impact toughness, causing it to decrease considerably. Increasing the aluminum content, the toughness of the material decreases. By analyzing the fracture surface of these steels, we were able to observe the transition between a fracture surface of ductile materials, 0 and 3 aluminum, presence of dimples, up to the fracture surface of brittle materials, the presence of cleavage. In the case of this manganese content, the transition between ductile brittle is when the aluminum content is 6% big weight. For the alloy family of 28% by weight manganese, the same trend is observed. Up to 6% of aluminum has ductile fracture surface, sign, look at this. From 6 aluminum, the fracture surface chance on the lid has characteristic of a brittle fracture surface. Leaving aside mechanical properties, we did not propose to study the corrosion resistance of FeMnAlC steel. For this case, we only did a study on 20 manganese signs. According to the state of the art, the increasing in manganese decreased the resistance to corrosion. To evaluate the resistance to corrosion, we study acidic medium, a neutral medium, and an alkaline medium. In this figure, the Tafel curve for sulfuric acid are represented, in which we observed that in general the behavior of FeMnAlC steels in this medium for any aluminum content is the same. When comparing with styrene steels, it is observed that there is a great difference, but in corrosion, density, and potential. It is clear that the behavior of stainless steel is much better than FeMnAlC steel. The same can be observed in hydrochloric acid, where the behavior is very similar, although among the FeMnAlC steels. The 3% aluminum steel has more anodic values in potential and lower values in corrosion density compared to the other FeMnAlC steels. In general terms, it is concluded that the resistance of FeMnAlC steel is lower than stainless steel. It is possible that by varying the content of aluminum and manganese, or by adding some other alloying element, a composition of FeMnAlC steel with high corrosion resistance could be reached. In the neutral medium of sodium chloride, 3.5% big weight, it is observed that there is no great difference between FeMnAlC steels in terms of corrosion resistance, and that, on the other hand, stainless steel is still much better. But in the case of an alkaline medium, the situation is a little different. Here we can observe that the behavior in this medium is very similar between FeMnAlC steel and stainless steels. Finally, regarding corrosion resistance, it is stated that the effect of the aluminum oxide layer is not versatile, and its behavior depends a lot on the pH of the medium. So throughout this year of research, we have some articles that are under development, others that are already under review, and others in the future. These are the following: effect of aluminum content on the dynamic recrystallization of this FeMnAlC alloy during thermomechanical hot forging treatment. This article is under review, submit in material characterization. Other is effect of aluminum content of the abrasive wear behavior of FeMnAlC alloys to be submitted. And other is effect of aluminum content on the corrosion resistance of the new FeMnAlC alloy system as a potential replacement for stainless steels under preparation. Another is mechanical properties, abrasion wear and processing in FeMnAlC 20H manganese alloy aluminum under preparation. And finally is a work about processing by hot rolling. This is about internship in Mexico. This is under preparation. In future investigation, we continue to discover some phenomena that are worth studying in this type of steels. In the future investigation that we have to develop, and according to the previous result, are the following: study behavior of FeMnAlC steel in aging condition and low stacking foul energy condition for grinding balls, and a study by Mossbauer spectroscopy and X-ray diffraction about spinal decomposition. How is the evolution of dry austenite, poor austenite, and phase carbide in function of heat treatment? Finally, in all this time of work, many new questions continue to arise as we find interesting results, which deeply awaken our interest to continue working on these types of steels. Thanks for attention. Gracias por la atención.
Gracias. Thank you so much. Thank you so much. Okay, grazie a voi. And so, very interesting presentations. There is a lot of work starting from very basic issues. So many years ago, I was also a Mossbauer man, but now I am not that much long. So I have understood most of your presentation from the topic of industrial, and I would say especially the use of aluminum for lightweight steels. It's interesting, and it's hopefully to be introduced in the future. So if some of the guests they have any kind of question, I think in an informal way, if possible, if you would like to ask, and if you'd like to answer, it would be nice. Otherwise, I will make some questions as well. If Maria, if you want to speak in Spanish, well, there's no problems at all, because we can understand Spanish, but we cannot speak. Like I can understand the French, like, but I cannot speak. Again, it's the point that, or we can keep on using English language, because after all it's very useful. So the weight of the sample, this is a very easy question. Normally you process how much weight in terms of grams, in terms of a kilogram, or what else. You have an induction furnace, and I think you keep the atmosphere in air by argon, is it? And then you can process yourself. This is the first basic question. Maybe it's a detail, but who wants to or maybe Oscar, you've been also working there, yes? As far as I understand, yeah. So,
well, basically, when I did my PhD, I use vacuum induction furnace to produce around, like, I will say 4 kilograms. That is the order of the weight that we are using.
Yeah.
Now we are trying to move a little forward with the process. So at the Universidad del Valle there is an induction furnace, and we are using right now like an open atmosphere. So even without nitrogen, so that makes more closer. It's closer to the industrial making process of the steel. So that's more or less the.
And you did not check any kind of oxides in the samples you did. It doesn't seem, because you would have got it from the Mossbauer spectroscopy data. So I think you have not the troubles about oxide formation inside the sample. Okay.
No, there is trouble with the oxide formation that becomes from the alumina. So when I did vacuum induction furnace, the quality was really great. But in this case, that the FeMnAlC that John and Sebastian produced, of course, there are some inclusion. There are some aluminum oxides inclusions, and also the surface of the ingot.
Yeah,
you have to remove the for sure.
This is normal.
It's normal, and inside
normal.
there are still some inclusions that is still an issue. For that point of view, there is still the need to make some further research in that area.
Yes, thank you. And may I ask a question about Mossbauer spectra? So is there any clear indication about the Mossbauer parameter? I say Mossbauer, not only Mossbauer, like should be said. The Mossbauer parameters of the kappa carbides, which is of the kappa. Do you have any clear indication about that, about isomeral shift and quadruple splitting? Yes, so you have a clear indications about that, because as long as I've seen, you have 3 components about austenite, yes, what we saw, and then a very little difficult to detect, in my opinion, sextet or sextet distribution, but basically it's a combination of singlets, which is my very first and basic impression. But if any of you would like to tell me some details, even in Spanish directly, speaking slowly, I can understand all. It's up to you, okay?
I don't know, John, if you want to jump in, or I can start and then you add some comments, or. Okay, so.
John, ¿tú quieres?
¿Cómo fue la pregunta?
The question is basically if those kappa carbides that we observe.
Yes, you can fingerprint. Yes, have a clear about those kappa carbides. So because this is the difficult thing to you have some X-ray diffraction data, then you have the Mossbauer data, but it's always difficult because it's not cementite, or it is something more difficult to identify. I like both X-ray and Mossbauer. I think they are very useful for material characterization at the academic level. Then you must go into the more standard metallography techniques, but I think it is very useful. So, il parametro Mossbauer del carburo scappa están precisamente determinados o no? Okay, this is the question. So, about the Mossbauer parameters about the kappa carbides, if you have any. So, if it would be possible in the future to have very, very clear indications. But no problems if we can even discuss other topics.
Well, let me speak.
Mm-hmm.
We make a previous work
Mm-hmm.
using this type of alloy.
Mm-hmm.
When we made homogenation at high
Mm-hmm.
temperatures,
Mm-hmm.
like
Mm-hmm.
1000,
Mm-hmm.
and then cool it quickly, quench.
Mm-hmm.
It's not. We observe the transformation of the austenite in 2 or 3 different, as
Mm-hmm.
the
Mm-hmm.
paper shows.
Mm-hmm.
With this here treatment, it's very difficult to obtain the kappa.
Mm-hmm.
The kappa phase.
Mm-hmm. Mm-hmm.
But when we make an aging process
Mm-hmm.
of this type of alloy,
Mm-hmm.
the kappa phase is induced.
Mm-hmm.
Okay, and depending of the time of the aging process,
Mm-hmm.
we can increase this kappa phase.
Mm-hmm. Mm-hmm.
That we observe is that the kappa phase appear as ferromagnetic one by Mossbauer spectroscopy.
Mm-hmm.
It's a preliminary work. However, we need to finish it in order to deduce if we can see effectively that the iron in the kappa phase increase or not. And we need to make also X-ray diffraction because X-ray diffraction can permit us to quantify the kappa phase. Mossbauer not. Mossbauer permits to know the quantity of iron in each of the phases which appear. Then this is the last proposal of Sebastian go in this sense to study systematically by Mossbauer and X-ray diffraction the kappa phase.
Okay.
Okay.
Okay. Thank you.
Para complementar,
Sí.
El interés principal de estudiar mediante espectroscopía Mossbauer estas aleaciones es precisamente que el fenómeno Mossbauer se da, entre otros elementos, en el hierro. Estas interacciones hiperfinas son fácilmente detectables por medio de esta técnica. Nosotros también hemos utilizado esta técnica para estudiar tempered martensite, martensita revenida por Mossbauer, y hemos encontrado que el desorden de la ferrita cambia entre los tratamientos térmicos. Entonces, esto nos permitió seguir estudiando, en este caso, los aceros FeMnAlC, mediante la espectroscopía Mossbauer, y encontramos que habían unas diferencias en las formaciones de las austenitas, tanto ricas como pobres. Los elementos alrededor del hierro permitían que el parámetro desvío isomérico del isomer shift fuera hacia valores más positivos o hacia valores más negativos. Entonces, dado que la descomposición espinodal, la formación de los carburos capas, es debido a la austenita enriquecida, entonces ver cómo esa austenita enriquecida se va transformando en los carburos capas por medio del seguimiento del desvío isomérico, pues sería un tema interesante a investigar para poder para poder determinar o para poder dar a entender que la espectroscopía Moss-Bauer es muy útil para este tipo de estudios, digamos, tan puntuales, de interacciones muy finas.
Muy bueno, gracias. Okay, thank you for the explanation. I think I got most of it, apart from my bad Spanish, of course, but it's my fault. And yeah, and Christophe, do you have any kind of question from your side, or Maria, maybe, if you have any question? Maria, you can ask in Spanish or in in English. As for you, Maria, she's living in the UK since, I think, 10 or 15 years.
Yeah. Thank you, Fabio. I'm Spanish, but been living in the UK. Yeah, I work in steels, not exactly on those ones. I work macroalloy steels and the austenitic stainless steel 316L. Just from your presentation, very comprehensive. I just got a question that you see you increase the aluminum level and the impact toughness decrease and the grain size decrease. Do you have, because usually when you observe a decrease in grain size, the strength decrease and the impact toughness should increase. Do you have an explanation for that?
You want to answer that, Sebastian, or
Profe, la última partecita de la pregunta no la entendí. ¿Entendí el aumento del aluminio disminuye la tenacidad?
Yeah,
yeah, which I saw in one of your graphs, in one of your slides, I cannot remember which one it is, that as you increase the aluminum level, the impact toughness decreases. And in the previous slide, you show the microstructure of the steel, and increase as you increase the aluminum level, the grain size decreases.
So it's expected that the decrease in the grain size that will provide a better toughness is basically the question.
Yeah, it decreases the grain size, improves the toughness, and improves the strength at the same time.
Yeah, there are two things there. The first one is related to the dynamic recrystallization. So as we increase the aluminum content, there are some ferrite formation. So that graph that you are mentioning is because when we produce a little volume fraction of ferrite, that serves as nucleation points. So as we increase the aluminum content, we will have like a better dynamic recrystallization process in the high aluminum side. So that's the reason why the grain size decreases. For one hand. To the other hand, it's expected, as you mentioned, that with lower grain size, we should have a better toughness. But probably the main reason of that is because at high aluminum content, we still have some issues with aluminum oxides, or maybe some microporosities or different factors that are decreasing the impact toughness. So it's hard to tell, but you have a really good point. It's expected that we should have like a better toughness, but probably the other factor of the difficult in processing those alloys in the high aluminum side is also preponderant in that case.
Yeah, thank you for your explanation. I see that there is another question related to the grain size, that you increase the aluminum, decreases the grain size. Have you observed any pinning particles? Is it because they have pinning particles that pin the grain boundaries? This is the last question.
Well, I did the ABSD analysis, and I didn't observe clearly the grains growing up around those particles. Probably those particles are in the range of micro size, or so that is hard maybe to detect at those zoom levels that I use to take the EBSD maps.
Yeah. Okay. Cristophe, do you have any special question, or if you want, of course?
Special question? No,
Yes.
but first of all, thank you very much for this interesting presentation. Works. Okay, my question would be the transposition of this work and application, because you also illustrate the application of nowadays. So it's very thin material, whereas we are working on very thick material. So do you have an idea of this transposition possibility? Typically to flat to long product?
I mean, if you want to make like a really flat and long product, is that what are you?
Yeah, your work is mainly based on also the application you showed before for flat products, very thinness or very thin thickness. Do you know maybe the limitation of this kind of alloys for bigger parts?
Well, that is a good question. I am not aware if there is a limitation regarding the thickness, but I know, for instance, this pattern that I show about the Armo product, they are using even without hot rolling, just directly casting. So they can produce really thick material without any processing. But yes, I'm not completely aware about there is a limitation about the thickness. Yeah.
So because for us it will be typically the future work we will perform this. Take this all the study you showed us as numerous study of the last years and try to see what is feasible for bigger products. So even bigger than the armor.
Yeah.
Okay.
So,
okay.
Yes, if I may say a word. So they are doing, you can split the production of steel in two big parts. So flat steel production and long steel production as for special steel. So if you are going to cast special steels by continuous casting, the maximum it's largeness, it is 250 millimeters, but they have loom casters, they go one of the biggest in the world, actually. They go up to, Cristophe, 700,
850.
800 round. So it's some would say 3 or 4 times more than a bloom caster comparing to a slab caster. So the slab caster, then you can reduce it by rolling, of course, and then you can reduce. But if you start from 150, then you will go, I would say, about 10, 20 millimeters without difficulties. You using, but if you have very, very large section, it's another point, maybe more challenging, by the way. I have also a question, because it could be also a sort of collaboration. I know, Cristophe, I don't know the compositions actually, but I know that in the future you could produce some special small size heats. I think a few tens of kilograms or the like. I don't know, a little bit larger than yours, but not as but would be possible in the future to make a sort of joint characterization in order to exchange your ideas. So Cristophe is working on the industrial side, so he's plenty of SEM, standard optical microscope. He has not X-ray or Mossbauer, which is felt, especially in Mossbauer. There is not any longer a lot of Mossbauer especially in Italy, because of the problems of radiation, and so no one wants to have to do with gamma rays. When I did my PhD, I had no dosimeter, and so I was working by hands with no one would do it nowadays, and even with X-ray as well. But this was unfortunately too many years ago. But if you want to exchange experiences or what else, because after all, sending samples, so it's not very difficult. We can send materials, small materials all over the world, maybe exchange experiences. And then this is from their own side. And about me, and maybe also by the way, also Maria. We are working in something related to making CALFAD tools useful for real metallurgical
Interesting, quite
calculations.
interesting.
And so we are sort of joint editors of a small number of the open issue, which is metals, but never mind about that. But I've been adapting to make it open in a way, which was in any case open, but for Thermocalc, the database that my colleagues Ben Halstedt and Alexandra Kwan, they made those databases for CALFA to make the calculation of phases. I've been adapting, I don't know how precisely, but I adapted them for another software, which is a little bit cheaper and maybe easier than Thermocalc, which is Pandat. And the file, by the way, is available, or we can work on this, because you can estimate what's going on about different situation. Of course, it's up to you to input the phases and so on. So you can type and change the phases, but it's very, very complicated. But as long as these guys, Halstead, Juan, and the others, they have done this high precipitation, high manganese, is nice, because this is open, so you can work on it. Otherwise, if you have other files from Thermocalc, they are closed. And they are commercial, and then you don't know what it's really the. Of course, maybe they could be more precise, but I feel that sometimes using open data or open possibly files that you can open, at least it's nice. So I've been adapted, and they are available. We made some preliminary work, even with Cristophe, with some master thesis a few months ago, just to know what it is possible to get out from this. I'm not sure you can detect all, because it is the experiments that determine the database, not vice versa. I mean, if you do the experiments and then you extract the phases, the kappa carbides, the other phases, then you understand the situation. But if you don't do experiments, you will never get anything. Okay, so this is, I think your work is very interesting, and also I am very fond, my future ideas would be to develop something, but and Cristophe knows it, to possibly cast a little bit more than a few tens of kilograms, because I think the sector is very vital, because you can do many kind of different things using cheaper elements, of course, Oscar, but even also for lightweight steels, which is vital especially in Europe. They want to make everything green and blah blah blah. So maybe too much, and so the situation is that. So thank you for your time. And I'm pretty satisfied by this first meeting, so we can exchange ideas and what else in several directions. One direction could be speaking directly with Cristophe. I will exchange your emails, so you can, and the other is that you can interact with me and also with Maria if you want, because speaking Spanish is already interesting. And so we are doing, but I think there is not too much time. But our interest is you have CALFA data, but we are not CALFAdists. I am not I am a metallurgist, not a CALFAD, but I want to exploit CALFAD to do real life calculations.
Really nice initiative.
Yeah, this is the idea. So we have some ideas about possible cracking, about grain size structure, which is the work of Maria. Maria, she has been working a lot, especially on copper alloys, but the principles are really the same. And we want to use this kind of approach for different kinds of metallurgy. I've been using it, for instance, even for semi-solid processing, for designing some experimental machines. So very pleased to interact with you. And now here it's around 7.
Eight?
Yeah,
okay.
Yes, going close to yes, we are close to the night here in Udine, I think even in Metz. And Maria, she's a little bit you have some light, yes, as well, Maria. You are in Warwick, you are in London, or maybe you are in between, I don't know. And it was because even thank you for your general presentation and also giving some details about where you are living and when you are where you are working. I hope in the future we can do something. I am something in between some practical aspects, and I have quite a good background many years ago, unfortunately, material characterization, and but I am from one side and the other. So from metals, I cover quite a lot of things. Okay, so all the best, and let's think to do something together. I will send you an email with the contacts of everyone here, and okay, it was very nice.
I just want to mention that I'm really happy with this meeting, and really thank you for the invitation and your interest in it. Yeah.
Yeah, nice papers, and I wish you all that your work is going in progress will be soon published. But it will be nice to even we are so far one another, because you, Oscar, you are in Canada.
Yeah.
the other guys are in Colombia. Maria, she's in UK. Cristophe is in France, and I am in Italy. So, but it's not so difficult to collaborate if there are some new ideas. And was very pleased that you accepted my invitation and so on. Okay.
Okay. Thank you very much.
Fabio, thanks very much for your invitation. It was very nice for us to show our work, and we are happy that you enjoyed the presentation.
Yes,
Thanks
next year, close to Udine, because there will be the conference organized by Austrian peoples on high manganese steels. Maybe we can study to present a paper, because for me it's 3 hours by train. For you, it's
a couple of
one day of flying and so on. Of course, if it will be online, no problems, you will do it. But if you want to consider this opportunity, I can go make a joint presentation, because it's organized by industry, but I think it is the guys that have already been active in France, in Japan. I think also, of course, in Korea. In Korea, I've been briefly staying there in POSCO University, but for a while, and I have good contacts with some guys there. For instance, Frédéric Barlat, who's a Frenchman that's working there in metal forming, and even Professor Badesha, that I don't know. I should visit him by Monday, but I am still puzzled because I have 2 vaccinations, but the rules in UK are different from here. Yes, Maria. Yeah. El Green Pass is not, so if you want to travel, you should do something else, which I have not yet well understood. So I think I will call him by making a phone call or a Teams call instead of staying there, because I'm a little bit worried that they stop me and I am stranded in UK and I cannot move. I use it a lot to travel by car when I am in Europe, of course. I've been visiting Cristophe in Metz with my car. It's from here to Metz, it's 10 hours, yes, or 11, or the like. We will meet with Cristophe next week, yes. We will go, and unfortunately, I cannot meet you there, because I would be pleased to have a dinner with you, but maybe in the future, one never knows, we will be able to move, okay? So, thank you again.
So
have a good day.
Bye.
Yes, a good night, you on the European side. Ok? Grazie, grazie a tutti. Buona serata. Arrivederci.
Gracias.
Bye.
Bye bye.
Goodbye. Goodbye.